So good afternoon to everyone. It's very pleasure to have here Federica Spoto. She spent some time here in Pisa, where she got her master degree and also her PhD under the supervision of Professor Milani. So I could also meet her in Pisa. Today she will speak about high precision asteroid astrometry, challenges and results. So Federica, when you want, you can start.
Thank you, Giulio. So good afternoon, everyone. I'm really happy to be here. Just a few words if you don't know me. So as Giulio said, I did my master's degree and PhD in Pisa, work with Andrea. I love working with Andrea. And then I moved to France. I spent 4 years in France, working with William, Paolo, and the Gaia team between Nice and Paris. And now I'm at the Center for Astrophysics, Harvard Smithsonian, and I work for the Minor Planet Center. So when Giulio asked me to be part of the seminar series, I was thinking about what to present, because being at the Minor Planet Center really faced me with a lot of new challenges in orbit determination. So for those of you who are not familiar, the Minor Planet Center is the institution that has been chosen by the IU to store and disseminate all the observations and orbits of asteroids. So basically, we receive a lot of observations that span different time span, like very short arc, very long arc. We need to link objects, and we have TNOs and we have NEAs, of course, lots of Bain belts. And I'm sorry, I have a cat as well. and we have natural satellites. So I really had to face with a lot of problems, comets that I didn't even think about before. So I was really, I wasn't sure about what to present. But then, since I'm also part of the Gaia team, I've decided to focus this talk on high precision asteroid astrometry for various reasons. It's because it's linked to a lot of work that I did starting from my PhD, and it's a huge project that I wanted to present and then I really love. And on the other side, it's because people may think why to spend all this time to work on some really high precision astrometry, but not a lot of observations. So the question is, what do they really matter? Will they change something in the view of our solar system right now? And I hope I will convince you of that. So the other point is that usually when I think about how to present these kind of results, I always think about if I have to start with Gaia and then the high precision astrometry, or if I have to start on what.
Un seminario high precision asteroid astrometry.
On how we.
Could you switch off your microphone, please? I'm speaking to everybody who is attending the seminar.
And so the idea is, let's start with the overall idea on why it's important to have this kind of high precision asteroid astrometry. And then I will explain you why those are kind of complicated to deal with and what challenges we had to face and what results we are having and what are the future plans, near future plans. So let's start with asteroid families. For those of you who are not familiar, asteroid families are in general the result of past collisions between asteroids. So you have just collisions between asteroids that happens all the time. Sometimes the parent body is completely shattered, and in this case we call a fragmentation event. And sometimes the parent body still exists, and so we call it a cratering. And I put a picture from the Dawn team. This is Vesta, the asteroid Vesta, and you can see the two different basins on Vesta, the two different older and largest basin on Vesta, which are the Rhea Silvia and the other one, which is called Veneneia. So the idea is that this is a cratering event. So you have a huge asteroid, this is hit by some other asteroid, and then what you have left is just a crater, and then there are all the family members that are going around close to the parent body. So we call the parent body what's left when something is left. Otherwise, we identify the parent body as the lowest number asteroid in the family. And then we have all the family members. There are some important properties that can distinguish asteroid families and that can allow you to find them in the main belt. They can be related to the dynamics, and so they share similar orbital elements, which are the proper elements. Or on the other side, there are physical properties. So, I mean, they can share some similar physical properties. As of today, this has been kind of remaining disentangled. So families are recognized using dynamics, and then you add whatever you know about physical properties, which is not a lot right now. And this is one point that I'll show you is going to change. So I saw you had a talk about proper elements for debris. So I think you have some ideas what proper elements are. So I'm not going to spend a lot of that. But the idea is that asteroid families have been identified for the first time more than 100 years ago. And then we identify them, as I said, using proper elements. Now, what you see on the left is a plot of the proper semi-major axis, the proper sinus of inclination, and the color code is given by the proper eccentricity. The idea is that this should give you an idea of a three-dimensional space in which you can identify this clustering. The idea is that you use the proper elements, otherwise in the usual orbital element space, the families will be completely blurred with the background, so they're not easily recognizable. How to identify them? We use some kind of hierarchical clustering methods that can identify clustering in different steps, and then they put together all the objects that we suppose belong to the family. Then, if some physical observations, physical parameters are available, like the albedo or the spectra, which means the colors, so the chemical properties of the objects, then we use them to identify possible interlopers, which means these are objects that we dynamically thought belong to the family, but they actually don't. As of today, in a work that, Zoran Knežević and Andrea did for a lot of years, I started during my PhD, we have identified more than 100 families. The whole list is available on the ASDAI's website if you want, so that's the link. Now, one point is how do they evolve in time? So basically, you need to think about this plot on the left as one screenshot. So it's like you're taking a picture of the main belt right now. And this represents how the situation is right now. It's not how it was millions of years ago. So it's the result of the evolution of this family over millions of years, because this family are not just static entities in the main belt. How do they evolve? This is a very easy sketch of how things should work. Now you can see on the upper axis, the semi-major axis, and on the vertical one, you have two time. With TC, I indicate the time of the collision. And when I say today, I mean what you see today in the belt, so the family that we are able to identify. So as I showed you in the picture at the beginning, when the family is formed, there is a collision. And then we have the parent body, if it's left or not. But then the smaller pieces starts to move in the semi-major axis. And they tend to form the current configuration. So the smaller pieces move faster. And this is the idea. The idea is that asteroid families tend to evolve over time. And so what we see right now is the result of the evolution. So one question that we had was, okay, so how do we go back in time and compute the time of the collision? This is what we call age of the family. So when I say the age, I mean when the family formed, so when the first collision that formed this family happened. And the idea behind is quite easy if you look at the plot. The idea is that the time of the collision is the delta A divided by this velocity at which the fragments move. Now, the velocity happens for some reason, and reason is a non-gravitational perturbation, which is called the Yarkovsky effect, that do a lot of stuff for solar system objects. One of these things is contributing to the evolution of asteroid families. So you can think the Yarkovsky effect in this case like an astronomical clock. So as I said, it's a non-gravitational perturbation. Maybe it's the most important one that acts on small bodies. I mean, asteroids. There are other non-gravitational perturbations for comets. And it's related to the anisotropic thermal emission of the solar radiation of the body. So the body is rotating, and then while it's rotating, is emitting this thermal radiation. It depends on a lot of physical properties. So just to give you an example, this is proportional to the inverse of the diameter of the object. And usually a lot of these physical properties like the thermal inertia, the density are not available right now. But the Yarkovsky effect is really important because its main effect is a secular drift of the semi-major axis. It means that this effect, even if it's really small, changes the orbit of the asteroids over long time span. So these are effects, of course, for MEAs, because changing their orbits will change the probability that they could impact the Earth. So it's something that you really need to take into account when you do impact monitoring. But as I said, since it's proportional to the inverse of the diameter, it acts on very small objects. So it makes the smaller objects in the family move towards different directions that depends on the cosinus of the obliquity. So we want to have estimation of the Yarkovsky effect. But as I said, since it depends on physical properties, it's very difficult to obtain it just from them. So we had to find a different method. And to do that, we use a Comet-like model for transfer acceleration. This is taken from a paper, an old paper from Marsden, and now the work has been done by Davide Farnocchia in the 2013. And the idea is that you can write this something that really looks like a very easy equation in which you have the transverse acceleration that depends on A2, which is the unknown quantity, the one that we want to measure, which means the effect of the Yarkovsky effect, and G, which is a suitable function of the heliocentric distance. Once you are able to compute A2 some way, then you can estimate the semi-major axis using a perturbative Gauss equation, and this is just the beginning. Then you can mediate on that one. So the question is, how do you detect A2 if you can't use physical properties? And we use a method that involves the astrometry. So instead of doing the usual orbit determination, we add one parameter, in this case A2. Then you can decide you can add as many parameters as you want. And then we use a 7-dimension differential corrector. Now, in case you're not really familiar with orbit determination and how it means, I just put something like orbit determination in one slide, especially least square feet and differential corrections. So the main goal of orbit determination is that you want to minimize the target function, which is the Q function that you see in red on the left, which depends on the residuals, which are, as you think, the observed minus the computed, and the number of observations 2 times, because you count alpha and delta as 2 different numbers. So that's why you need to multiply by 2. And then something which is called the weight matrix. Now, I put it here. I will put it again at the end, because it's something that it's really important, and I really worked a lot on that. It's a huge part of this talk. So the idea is that usually the weight matrix, it just contains the weight that you will like to give to the observation. So you can imagine like really every small 2x2 matrices, which contains on the diagonal the variances, I mean the weights, and on the other 2 sides you have the correlation in alpha and delta. This is done for every observation, so that's why you have the number from 1 to m. So usually a normal weight matrix doesn't contain correlation. So the weight matrix that you normally use is just a diagonal, which contains all the weights on the diagonal. I put the whole matrix because I will mention something about correlations when I will talk about Gaia data, and then how they really influence the orbit determination then. So just take into account that this matrix will play an important role later. So the idea is that we want to find the minimum. So we look for the stationary points of the target function. We use matrix which are called the sign matrix, that are just the derivative of the residuals with respect to the parameters. Now, with X, you can indicate all the parameters you want to fit. So if you are talking about a usual normal determination, usual orbit determination, just think about the 6 parameters that define the orbit. In our case, that's what I mentioned before. When you want to detect the Yarkovsky effect, what you do is that you add a parameter, which is not painless when you want to do it. It looks really easy, but it's not. But actually, that's the idea. So you are adding parameters to the orbit determination. And then what you have is just you want the solution using the differential correction. So you just want to determine how much you need to change your solution to converge to the real one, to the real orbit, using the covariance matrix and some kind of matrix multiplications that always involve the weight matrix. So that's the point. Important thing of that is that you have also as output the uncertainties of the orbit on the orbital elements. That is something that I will show you later and then will become useful. So what we did over the course of some years is that we tried to detect Yarkovsky from the astrometry. Now, some point about that. It's pretty complicated because you need small objects, as I said, because otherwise the Yarkovsky effect is negligible, and you want accurate orbits. Okay, when I see accurate, I mean an uncertainty on the semi-major axis of 3 times 10 up to the -9 AU. So you want a few kilometers. The idea is that you want to be able to use just astrometry to detect Yarkovsky, so you don't want noise. And then if the orbit is not good enough, it might be noisy. So as I said, we use the 7-dimensional differential corrections. It means you use an existing orbit, you fit the orbit to the observations, and instead of just retrieving the 6 parameters, you have the A2 parameter. Once we do that, then we want to check that the result is good. There are 2, let's say, parameters that we use to do that. The first one is the signal to noise ratio, as usual. So it's the ratio between the absolute value of A2 divided by its uncertainty. And usually we want it to be larger than 3. And on the other side, we check on something which you might see as physical reliability. So the idea is that you can find a meaningful Yarkovsky effect from the astrometry. That doesn't mean that it's physical reliable. So if, give an example, if an asteroid is large, I mean, around 4 kilometers, you can't expect to find a large value of the Yarkovsky effect. So this is something that you want to check, because that might be the astrometry still too noisy to produce some reliable results. So the state of the art is that with Davide, we work on that, with Alessio, so it's here, we work on that in 2018, and then Greenberg, with Jean-Luc Margot, they work on the same subject. So it's still it's an open program in the sense that people are trying to detect the Yarkovsky effect for the largest sample of objects which is possible. Once I told you it's because of planetary defense, because you want to check it for the impact monitoring. And the other one is that we want to have a sample that will allow us also to understand, to retrieve physical properties computing the Yarkovsky effect. So you can think about the opposite. If you start from the Yarkovsky effect from the astrometry, then you can go back and try to understand how the asteroid is rotating, or the density that it has, or something like that. So as of today, we have more than 200 detections, and actually they are updating continuously. There's one point, though, that if you look at the plot on the left, should be kind of clear already. The plot shows kind of the whole asteroid population. I mean, it's truncated, but it's the majority of the asteroid population. And on the x-axis, you have the semi-major axis uncertainty, and on the y-axis is the diameter. So the yellow box indicates which asteroid you could think that could have a detection of the Yarkovsky effect, because they're small enough and they have good enough orbits. Now, if you look at the color, the blue points are NEAs, and the, I don't know to call it pink or light red or something, they're MBAs, so main belt. The point is that all the detections that we have up to now, they correspond to NEAs. So why is that? Because as I said, we want accurate orbits, and an easy way to have accurate orbits is to have radar observations. And you can only have radar observations if the object is close enough. So when it has close approaches, and so the radar doesn't go to the main belt, that's the point. So that's why until now we had this kind of limitation. And it's a huge limitation when you study asteroid families, because as I said, now that we understood what the Yarkovsky velocity is, the point is, how do we compute it for a given family? Because we don't have any estimation of the real value. And then the other point is, how do we compute the spread in semi-major axis, which we call delta A? So this is what we started with Andrea and Zara in 2015. And if you remember the plot I showed you about proper elements, that was, you could identify families in like these clusters. Then if you look at, you just take one family and you look at the family in another plane, this plane is the semi-major axis and the inverse of the diameter, which means the largest object goes to the bottom and the smaller objects goes to the top. What you see is what we call the V shape. So families tend to assume this kind of V. This is due to Yarkovsky, because as I was saying, Yarkovsky moves faster the asteroids which are smaller. So they tend just to go and do this kind of shape. So the idea is always the same. It's pretty easy, the idea behind. If you want to compute the time of the collision, you just take the space and you divide it by the velocity. Now, for the space, that's the computation of the inverse slope. So I'm not going into details. If you have questions, I'm happy to answer to that. But the idea is that the algorithm that we applied in this case is exactly very close to a typical orbit determination algorithm. So we use nonlinear least squares with a weight matrix and we define weights. And then this is how we fit the two sides. And the two sides are fit in a separate way, so they are not connected. And then the other point was, okay, how do we define the velocity, which means the Yarkovsky effect that acted on each family? And we found this kind of formula, which is just a calibration, or better, we rescale the Yarkovsky effect for each family using the Yarkovsky effect that we have for Bennu. Now, Bennu, I think you all know, is the target of the OSIRIS-REx mission, and is the NEA for which we know best the Yarkovsky effect. I mean, the signal to noise ratio a few years ago was 200, now I suppose it's even more than 200. So the idea is that now another important thing is that when we computed it, we still didn't have the results from the OSIRIS-REx mission, and actually when it went and it computed the density of the object, we saw that the density was really compatible with the value of the Yarkovsky effect that we found, which is a very good validation of the math. So the idea is that, okay, we take this asteroid, which is the one for which we know best, we rescale it according to some of the physical properties that we can find. So we use some benchmark for the density class, and then we try to rescale it using some values of the bond albedo related to that. As you can imagine, this will introduce large error bar in the family, in the computation of the time of the collision, so in the computation of the age of the asteroid family. But there's one good thing. So the first one good thing is that we have now a method. So we started having this method that can uniformly compute the time of the initial collision. So it's really, you can apply it to every family once you found the family. it doesn't require manual intervention, which is something that I'll tell you why it's important later. But on the other side, we still have a lack of knowledge of physical properties. So we guess some of them, I may say that we guess some of the values, but we're still not convinced that they were the best values we could use. And the other point is that, as I said, we have no detection of the Yarkovsky effect in the main bulb. So this was really a limitation. And when I started working on that, we were like, okay, so what is going on? But on the other side, as I said, with this method, we were able to compute ages for more than 50 families. Not all the 100 families, because you require a family to be large enough to have a statistical significance on the border. Otherwise, the fit is not really good. But sorry. But we did it. And at the beginning, when you just compute one age at a time, you don't really realize what you're doing. But when you plot them all together, you realize that you're building something which is very close to a chronology of the main belt. So each point, each star that you see here represents a family, the time of the collision of a family. And the bar represents the error bar for the family, for the age. Some might seem small, they are not. It's just the age, it's just the family is young. So it's really, they're compatible with the age, but they're still pretty large. But on the other side, what you see is that you go from very young families. When I talk about young families, I say that their age, that they're younger than 100 million years, but not really, really young. I mean, they're still older than 50 million years. I'll explain you why this is still a problem. And then you go up and you go to primordial families. So if you look at the timeline on the bottom, you can see that some of the families, some of the age is really close to the beginning of the solar system. So, I mean, I did all of this to show you that what we want, we would like to have at the end is just an overall chronology. When we have all the families, we will have good measurements, the Yarkovsky effect. We will be able to reduce these literally error bars and just try to understand all the collisional history that went into the solar system, starting from the beginning until very young families. Now, a few comments on the plots. There are some points that you see there are 2 points on the same line, or even 3 points on the same lines. It means that we were able to identify different age for the same family. It might be due to different reasons. So for example, you have a family inside your family, or as in the Vesta case, you have 2 different cratering events. So the age that we found were almost 1 billion years ago and 2 billion years ago. And this is the same, that more or less the same that I estimated from the craters, the 2 largest craters on Vesta in this independent measurement. So that was pretty good result for us as well. And then, yeah, that's the idea. Primordial families, of course, have very large error bars. So what are the limitations of this, of all this plot? I mean, all this work. As I said, the uncertainties, they're too large. So this is not a real chronology because ages overlap due to their uncertainties. And then we still have a small number statistics because 50 families is not enough to really describe what was going on in all the solar system. Other point, as I said, the hierarchical clustering methods that we use, they have some problems in identifying very old families, like the primordial families, because they're, as I said, since Yarkovsky moved their elements, they are scattered all over the main belt. And so it's really complicated to explain to a hierarchical clustering method to go and find those elements and put them together. And very young families because they are too small. And so we lack this family in our sample, and this is pretty clear. So the question is, we know that we lack very young families. The question is, we lack primordial families because the HCM wasn't able to find them because there are not so many of them. So there are a lot of interesting questions about primordial families and how to find them and how to compute their age. Also because if you're able to remove all the family from the belt, the idea is that you're also able to find the primordial asteroids in the belt, which is something you really want to study to understand what happened at the beginning. So here, I mean, this view looks like a huge introduction, but I hope it really explains why having high precision asteroid astrometry is important. Because it's the only way in the main belt that we have to overcome this limitation. And so before Gaia, we didn't even think about the possibility of having something like that. But now I'll show you that we can. Then there will be also LSST, and now it's called the Vera Rubin Observatory, that is going to discover millions of asteroids. This means that what I call our small number statistic won't be small anymore. And then also Gaia is going to produce a taxonomic class for the object it's going to observe. We have people digging into surveys data to find all the possible physical properties that you couldn't find from them. So the idea is that we have a lot of unexplored data that we can still use, and there are also new methods like all the machine learning algorithm that can be also applied to help the hierarchical clustering method when it's failing. So let's try and see why having this high precision astrometry will really help us and how. So a few words about Gaia, if you're not familiar with it. I think you heard about that at least. Gaia is an ESA. It's a space mission of the European Space Agency. It has been launched in December 2013, and it's starting its operation mode. So it means scanning the sky in January 2014. It's in the L2 Lagrangian point. And the mission officially started, I mean, the data officially starts from July 2014. At the beginning, there were 5 years of mission. Now it's already been extended. Now ESA extends mission 2 years and 2 years. So we will see, but we're pretty confident that it's going to reach the 10 years that we expect. You have a picture, a plot that show how Gaia is scanning. So the red dot line represents Gaia scanning motion. You have the spin axis. So Gaia spins once every 6 hours, and the telescope try to sweep the whole sky. Is not really the whole sky, because you see inside the cone, Gaia won't observe. So the cone represents the limits of Gaia observations, basically. And the amazing thing is how that we receive the observation. And so it focuses the light inside a single digital camera, which contains 1 billion pixels for 160 ZDs. So just a note, it's the largest flown in space. And this is an idea on how the CC here spread. So you have all the, I don't know if you can read it, but all the AF and SM are related to astrometry. So it means they will give you the position of the object. And the others are related to the spectroscopy, I mean, colors and magnitudes and stuff. That's how Gaia works in general. Gaia has data releases. So there is no proprietary period for Gaia data, which means that all the data that we have has to be released to the community when they're ready. We receive them, we validate them, and then we give it to the community, which is something that I really appreciate from the mission, just my note. And the first data release was in September 2016, and we can say that it was just an appetizer on what the star could have been. So the main goal of Gaia, as I think you heard, is to produce a 3D map of the galaxy. And so it's really focused on stars, but on the other side, it's observing asteroids. So this is just a plus for us. The second data release was in April 2018. And now we had a third data release, which is called early data release, because it doesn't contain all the products Gaia wanted to give. It contains just a small part, which is only related to stars. Now, numbers are crazy. That we talk about billions of positions and proper motion of stars, colors, and parallax and proper motions. So this is something really amazing. But what you can see in here with the red dot is that for the first time in April 2018, we had asteroid observations in the release. So it was the first time we saw what Gaia was able to do with asteroids. And it is the first time the community had to deal with the high precision asteroid astrometry. I mean, the community and us before the community, we had to deal with this kind of high precision asteroid astrometry. But it's not bad. These are the post-fit residuals for Gaia and Gaia DR2. Just to give an idea of the sample, there were not so many objects. There were just 14,099 objects, 81 NEAs, just 2 trans-Neptunian objects, and all the rest were main belt. Numbered wave belt, which means their orbit was already known, well known most of the time. But the total number of observations was 2 million. And the other point is that the time span by the observation was 22 months. So if you look at the plot on the left, this represents the residuals, the post-fit residuals on the sky for each observation. So there are 2 million points, okay? The density is just the density of the beams, so how many objects you have in each beam. This might look weird because I just said, okay, let's say maybe it might look weird if you have an idea on what's the uncertainties on ground-based observations usually. Otherwise, you might just see that and say, okay, this sounds kind of good. It's not bad. There are some features that are kind of peculiar, but other than that, maybe there's something that we can use. So I show you that if you just look at this plot, this doesn't look so different from what you see from ground. So the question is, okay, you talk about high precision astrometry all the time. Where is this high precision astrometry? A few points before moving on. The feature can be explained. This is just an asteroid in the DR2. It's a main belt. It's called Amicizia. And what you have is just, these are all the transits. So, I mean, with transit, I mean a set of observations in a limited time span. And the plot on the right shows the same with the uncertainty ellipses. So they're focused on the center of the object, and then you have the uncertainty. Now, the uncertainty ellipse is really, really thin. And the fact that they move towards, I mean, that they go with the transit is because what is very strong in Gaia are the correlation. So what I told you at the beginning when I was talking about the weight matrix is that usually when we give weights, we don't give correlations because we don't know them. And most of the time, big survey stuff, they don't really know how to compute them and they don't really affect the astrometry. But in this case, Gaia does it. I mean, the consortium that work on the data, we produce them. And so when you look at the objects in alpha, delta, or in the sky, alpha, cosine of delta, and delta, what you need to take into account is that in there are correlations that need to be kind of removed if you want to understand how really accurate Gaia is. And this is what you can do. So if you get this plot on the left and you rotate the alpha delta into the along scan and across scan plane, which is the plane in which Gaia is observing, what you see is that the accuracy is basically all along scan and across scan doesn't, which means that if you follow one point on the CCD that I show you, the point will just move towards the CCD. We're able to identify the along scan position very well. We just have errors on the across scan position. I mean, the across scan position is more uncertain. We don't have errors. Sorry. What is really, really good is that here we reach the level of 1 mass, which is something that we never reached from ground. I mean, we never saw. So if you do the same kind of trick using all the observations that I showed you at the beginning, this is how the plot looked like in the post-residual plan along scan and across scan plane. And what you see is that now the accuracy is all in the along scan direction. So the across scan just span 100 mass, which are like 10 a second in total, even though the majority of the observations are in a smaller interval. So there are some challenges in using this kind of data, and they're all related to the orbit determination. So what I show you is just least square and differential corrections algorithm. But there are different things that go inside when you really do orbit examination, like you use ephemeris from different sources, and we were used to use ephemeris from JPL. Gaia actually used ephemeris from Paris, so use the IMPOP. And so we needed to check how was the difference and if there was any difference or if there were some problems using one or the other. Then you need to be sure about the relativity model you're using. I mean, you need to check everything that usually you think is too small. It produces an effect which is too small to be considered in the orbit determination. This time you can't do that because every small effect will change the mass residuals of something, and you don't want that. So something like similar to that as the perturber asteroids. So usually the orbit determination we use the 8 planets plus Pluto plus asteroids in the belt. And this depends on really what you want to compute. With Yarkovsky, there were 17, then we moved to 23, there was study behind that. And then other problem, since you want to compute the residuals, you want to check that your propagator, it's really good, and it's at least compliant with the Gaia, with the Gaia precision, with the Gaia accuracy. And so this is also a huge part of the work that we did when I was in this. So now let's zoom and see how it looks like. This is how it looks like. So you see that the majority of the object uses the density. So the denser part is between -5 and 5 mass in a long scan. And this is for faint objects. While for bright objects, we can reach the -1 mass. That's a feature which is usually nice. I don't know if you can see it, but usually you can see a small horizontal line close to 0, which is denser. This is because Gaia sometimes pass from the 2D window for bright object to 1D window for the faint objects. And when you have 2D windows, the observations are more accurate. That's why in a cross scan you have this kind of denser space. So how to put everything all together? So I tried to analyze the along scan across front residuals with the alpha delta residuals and what we have now from the ground. So instead of doing the overall rotation, we just wanted to analyze the AL component on the delta alpha and delta delta. I mean, it's alpha cosinus of delta and delta. And this is what we find. Dots represent the typical post-fit residuals. So I just got residuals for all the observatories, and this is a subsample of that. Otherwise, plotting all of them, it would be too denser and it wasn't easy to distinguish. But this is the overall behavior. And what you see is that the denser part is around the red circle, which is mostly about 500 mass. So from ground, we have more than 200 million of observations, which have a typical accuracy of 500 mass. And we have more than 2,000 observations, radar observations, which are very accurate, as I was saying. But then you can see the small red, small red cluster close to 0, and this is Gaia. So this is the projection of the residuals in the along scan plane on the sky. And then now, as you can see, these are really good. And so what we have from Gaia is that we have this is what's from Gaia DR2. We have 2 million of observations really accurate. So Gaia is usually 100 times better, 2 orders of magnitudes better than the typical accuracy from ground. And just to give you an idea, the next data release, that will be the DR3, that will contain asteroid observations, will contain almost 20 million of observations of the same quality. So this is what we are this is what we need to expect for the future. So what can we do with Gaia? That's something that we ask ourselves. Now, if you plot the orbit uncertainty, on the left, you have Gaia versus the state of the art. That was done for a paper we wrote for Gaia in 2018. So that was the situation in 2018. Now you can imagine that the orbits from ground, they just shift a little bit towards the better uncertainties because we have more observations. And still, you see that there are some objects that even using Gaia only were better than the uncertainty was better than if using all the available observations. But on the other side, the vast majority is over the line. So how do we use it? I mean, we also did some simulation in which we show that with 5 years or 10 years of Gaia, the thing really are going to improve a lot. But still, that's a problem, which is what we can call the short time span. I mean, 22 months are really 1 year, and it's not a lot. And even the next one, that won't be still a lot if you want to try to do something like detect the Yarkovsky effect. So you can't use Gaia alone. You need to use Gaia and ground-based observations. You need to combine them all together. So this is an example on how small is the sample of Gaia observations in the R2. We compare of all the available observations. So it's kind of a pity to lose information. So you want to use all the things that you know. So this is just an histogram of the observations of Phaethon over the whole time span by the observations. And I mean, the huge peak that you see in 2019 is because it had a close encounter with the Earth, and so everyone was observing it basically. And those red points, I mean, our bars are related to Gaia. There are 2 observations. So, I mean, it's like when you add radar, you have just a few observations, very good observations, but you can't really use them alone. You want to combine them with the ground base. And so this is what we wanted to do. And this is where things started to be a little bit complicated, because we are going towards a large sample of objects. So what usually is done when you want to detect this small perturbation, and when you want to work with a target of space missions, is just you analyze the astrometry for that object very in detail, and you work on that. And JPL, I mean, Davide is really good in doing that. And you can really understand which one were the worst one, which one were the best ones, and what to use in your sample. And it is something that you can do for just a few amounts of objects, but you don't want to do that for the whole Gaia sample in this case, or for the whole sample you can imagine. So you really want to reduce the manual intervention as much as possible, or at least this is what what we focus our work at some point, because we wanted to use Gaia, we wanted to combine Gaia with the ground, and we just realized that it wasn't so easy. You couldn't just take them and putting them together, because the accuracy were too different and Gaia were too many in a short time span. So you really needed to understand how to deal with all of that. And as I said, one really important point was the weighting scheme. So we start thinking how to improve. I mean, the weighting scheme is related to understand if an observation is good or bad, and it has been created. I mean, the outlier rejection was created, I mean, at least for our field, the software I'm using. It's been created by Carpino in 2003. Then the error model has evolved, but it evolves always in the same way. So what we thought is that, why don't we use all the available information that we have, because we have the residuals, and the residuals are basically an information on how the observatory performed over time. And so we grouped these residuals by observatory code, year, stellar catalog, and magnitude class. Now, I mean, observatory code and year, I think it might be quite kind of clear. Stellar catalog, it's something that, I mean, it really changed the quality of your observations according to the stellar catalog you're using. So when people started using Gaia, things really changed. So you want to take that into account. Then magnitude class is because sometimes it's easier for, I mean, at least smaller telescope to observe bright objects than faint objects. So your performances can change a lot when you do that. So you need to take into account. So what we had at the end of this analysis is a kind of huge file containing more than 40,000 lines that gives you all the RMS that you should use for a given observatory when you have these conditions satisfied. There are also all the different way of treating the fault, and in case you don't find this kind of all the conditions all together. But I highlighted the last part because now that I work at the MPC, I also have the possibility, at least for now, that will be available to everyone, but to check what the observers sent us, because when they send observations, they can also now, with the new format of the observations, they can tell us which was the quality of the observations when they did it. And so this is a kind of validation of the error model. And so if you look at the last slide, this is the closest one to 2021 that we have. And then if you look at the residuals that we obtain, I mean, the weights that we use, they're really close to the RMS sent by the observers. So the way in which now we work is that we usually use our error model as a default. What we do is that we use the RMS given by the observers only when those RMS are larger, because it means that the observer knew that the night had some problems, that observations were complicated or something. So it's better to use that information. Now, to give you an idea, so the plot of the numbers, what you see here is the same sample of data that I showed you for our error model. And then the color code represents the year of the observation, and the size represents the number of observations used to produce the statistics, because it's also true that if you don't have a lot of observations, maybe the statistic can be kind of poor. And what you see is what I was telling you, that this is the Atlas Observatory, and they're starting in, I mean, the sample that I have, that I used for the plot started in 2014, and then they were using a given stellar catalog. Then they moved at some point using Gaia DR1, which is the U, capital U. Then they moved to Gaia DR2, which is capital V. So if you follow the diagonal, you see that their performance is improved a lot over time, for reason related to the telescope, of course, but also for the use of a different stellar catalog, in this case in Gaia. So if you see at the end, when I think that everyone learned how to use Gaia DR2, and they also made some, modification to the telescope or whatever, the values that they find are really good. So with this kind of error model, which really takes into account a lot of different variables, the manual intervention that you require is known most of the time, or really small, now that we kind of fix all the parameters we needed to. And so we started using an MPC for all the different procedures that we want to use. So orbit fitting in general, NEOCP, which is the annual confirmation page, very short orbits, and TNOs, trans-Neptunian objects, and it's performing quite well. We are also collaborating with the Helsinki group, and they're using that for the asteroid mass determination. So they're having some very promising preliminary results. So this is something that we use. And also we try to detect Yarkovsky using Gaia DR2. I have to confess that our goal was to find a main belt. We didn't, because it was too soon, and the main belt we had that were too large. But we found some interesting case. Now, Bennu is not in Gaia DR2, it's just we use it as a benchmark to prove that everything was going well. So you need to find the same value for Bennu that has been found by other papers like Alessia's or Davide's paper or the Osiris Rex team, just to be sure that you're doing things right. And on the other side, we found some interesting values. What I said is exactly that. We did, it's nice to have new detection of the Yarkovsky effect, but it wasn't the main point of the work. The main point was to prove that we can do that without touching the astrometry. So we can just retrieve all the observations, just give it to the software and say, you do it. And we found some cases that were not possible before Gaia, and people were waiting for radar observations. So that's another way of saying Gaia can be our radar for the main belt. And then we found some methods to compute, we improve some already existing methods to compute densities using Yarkovsky. And this is what we really wanted to do. So the point is that we started using that as well for stellar occultation. So this is a work that's been done in collaboration. So your collaboration is with Manius and universities, with Nice, Paris. It's really a huge collaboration. And if you don't know what an occultation is, it's basically when a asteroid passes in front of a star and it blocks the light. So what you see is that the plot on the right, you can see the light. At some point you don't see it, you see it very feeble, and then you see it again. And usually they were used to determine the size of the object in the past, because the astrometry wasn't really good, because the astrometry of the star wasn't really good. But now the astrometry of the star improved thanks to Gaia, so we can think stellar occultation as very accurate point, very high precision astrometry, sometime in space for a given object. And this is just to show you that we did more or less the same work that we did with Gaia, using all the available observations and occultation only before Gaia, and then re-reduce after Gaia. And then, as you can see, things are moving down, which is good, but still occultation are not a large number. So this is why it's good, but it's not enough. And still you want to combine occultation with ground-based observations. So Gaia, thanks to Gaia, we saw a huge increase of the number of occultations in time. This is shown by the histogram on the left, made by Paolo Tanca. And then this also helped the use of Gaia. I mean, both Gaia observations of asteroid and Gaia stellar catalog helped a lot in the prediction and in the observations of the occultation events. And also the diameter values decreases. I mean, when you look for possible targets of occultation, at the beginning, people were looking at kind of large objects because they were easy. But now you can also look at smaller objects, which means NEAs, so that you can improve the orbit. I mean, it's both. You have an improvement in the orbit, so you're able to predict better the occultations, and then once you have in the orbit, it's even better, and you can use them to refine the orbit. And so, I mean, in all those cases, Gaia and radar observations were necessary for the prediction of small NEAs. So this is taken from Gaia image of the week, and it's also part of a planetary defense talk of Paolo, a poster of Paolo. But the idea is that we applied, I mean, there's been one occultation event of Apophis recently. And what happened is that we used this occultation event to prove that we can refine Yarkovsky. So here there are different measurements of Yarkovsky effect. The light blue, it says it's theoretical estimates from the model. All the other green is other data, which is optical and radar. And what you see inside the smaller box is what we did to understand how good it was to have these occultation events. So the green is still the best measurements available in January. Then the blue one is when you add optical data from the close encounter. Then the other blue-green, it's you add radar. And then the two, I mean the red, and the other one, the D event, is the comparison between what we were able to find with our software and the JPL solution. And that's the main take-home message. I mean, the idea is that the red point is obtained without even knowing the astrometry. So you don't really care about it, you just use it and see how it's going. So we can use it with other targets of occultations, like, I mean, we're working on other targets like Didymos, which is the target of the DART mission, and also Phaedon that had several occultations in 2019 and 2020. So I'm done. That's the I mean, conclusions that I wanted for you to kind of take home, is that we're living in a very interesting times, because we are seeing something that we weren't able to think about before. And so we can work with high precision astrometry, and we can have it not only for NEAs, but we can go back to the main belt. And this will open really new perspective in the whole study of asteroid families. Also, we know that we will have to deal with a huge amount of data, and because of the forthcoming observatory like the Vera Rubin. And so, as I said, this has multiple challenges that are really fascinating. And one of our goals is to reduce manual intervention as much as possible. And I mean, all the work. So it's from the finding asteroid families to computing the Yarkovsky effect. I mean, we really would like to be able at the end to explore all the data we have to understand what was going on at the beginning of the solar system. And so we are trying to get ready to what will come. And I really thank you so much for your attention.
Thank you, Federica, very much for this exciting talk with great results. So now we have time for questions and comments.
What's too much altogether?
Well, let me ask a question. So, yes. Federica, thank you very much for this very nice talk, nice presentation about these results. So my question to you is, the main belt, you know, and if you look on the on scientific studies on the main belt from a dynamical point of view in the last years, the attention was more on other topics. So my question to you would be, what kind of dynamical problems or dynamical insights would you expect with this huge amount of new observations on objects, dynamical studies in the main belt? That's my question.
So, I mean, one of the things that we found out, it's a work that I did with Valerio Carruba last year, a few years ago, that was very interesting, is that using Gaia, actually, we were able to prove in some sense that the formation of asteroid families, not just, I mean, I told you that we have an impact and this is how families are formed. And this was not completely true. So it's an ongoing process, because then you have other kind of splitting or having small pieces of asteroids just moving around at the beginning. So it's an ongoing process. It just doesn't stop with the first collision. So the idea is that since we are missing a lot of these very young families, we don't really know what's going on at the beginning, because what we see after Yarkovsky is that, okay, this is the shape that he has after millions of years. But something pretty interesting is what was at the beginning. So how it starts forming, as example, ejection velocity or something like that, and having a large sample will really help us in doing that. And also, since LSST is going to discover small objects, it will be easier to identify this kind of family. So this is an example of something that we could work on.
Thank you very much. And let me also take this opportunity to advertise a topical collection on celestial mechanics about dynamical studies in the main belt. And I think it would be worthwhile to think about some results, even publishing there if they are related to let's say, to more dynamical aspects of the study. Thank you very much.
Thank you.
Thank you, Christoph. Okay. So other comments or questions?
Can I add a comment?
Yes, sure.
I just wanted to add, thank you, Federica, for the talk. Just want to reiterate on the last thing that she presented, because as Federica mentions, we're also involved in the occultations campaigns. So recently we had Apophis, which became essentially the smallest object ever to be essentially improve its orbit by this method, by stellar occultations, after 3 successful observations, essentially. And it was amazing. And it also contained lessons there with regards to all these small things that, as Federica said, usually you would disregard when you do astrometry from ground. And there we were actually digging into the milliarc second regime. So for example, you have one successful occultation observed in the US, then used that to get a prediction for the event that would cross Europe several days after. We went there to observe it, following exactly the solution that we expected, and we missed it. Then 2 days later, another event was predicted and successfully observed in the US, and we could trace back the whole 3 observations arc and see, for example, that there was some problem, some small error in the astrometry of the first star that biased the second observation. So all this, there's a whole new learning curve to be followed for when you go to such small sizes and such fast events, which is really exciting for this topic.
Yeah.
Thank you, Clemens. Okay. So How many main belt asteroids do you expect to observe in the next years?
You mean like LSST? So LSST talk about 6 million in total of new asteroids. So I mean, when they will come, they will more or less clean the space, I think. But at the moment, we are about 1 million, more than 1 million orbits in total. And then most of them are main belt. I mean, 20,000 RNAs or something like that. Maybe a little bit more right now, but.
Which is the accuracy for LSST?
We still don't know. We made some statistics with them. They gave us some weights, but it was very preliminary. There will be good observations. I mean, good observation from ground at least, and since they're using Gaia. If you use Gaia from ground, you are a good observer, so you know really how to reduce your data. You can reach something like 30 mass, 40 mass, which is good.
Okay, yes, because you are digging the ITF, you know, and using our preliminary initial orbit determination methods, and then okay, the accuracy impacts a lot the capability of this method to find out the solution. So for us, these new results seems quite exciting, and so we opt for better accuracies also from the ground. Okay, thank you. Other questions or comments?
Oh, hi, Federica. This is Jorge Perez from Mexico.
Hi.
Yeah, so for example, you said that there was this blind side to the Gaia observations. There's this cone region. Is that region fixed, or does it change over time?
Oh, no, it's always like that.
Oh, okay. So you can never...
Basically, you can't observe where the sun is, so it's not observing towards the direction of the sun, and the opposite one. What it changes is the scanning law, that changed. So it changed the way in which it's observing the sky, which is observable. That does.
Oh, okay. Okay, great. And
but the cones are really small. I mean, it was something that it was known since the beginning, and that they don't really affect. I mean, also because the goal of Gaia is not. I mean, it discovers asteroids. We have a program which is called Gaia Fun, and it can discover asteroids. It wasn't just the main goal of the mission.
Okay, great. Thanks. And also, do you expect your new weighting scheme to be able to be combined with other missions, for example, NEO Surveyor or LSST observations or NEO-WISE?
Sure. Yeah. The idea is that we use all the available data, so it will be updated every time we will have available. So right now I'm doing a study for the test mission, for example. So every time we have data, we can update it with whatever it's available. And if they give us RMS, it's even easier to understand how close we are or how far. So this is an help from both sides, let's say.
Okay, great. And just last question. So, sorry. Okay. Maybe I'll remember later, but great talks.
Okay.
Great talk.
Thank you.
Thanks a lot.
Thank you. Okay. Okay, so you are still in time for another question or comment. Okay, if not, I would like to thank again Federica for the nice talk. Thank you, Federica.
Very much. Thank you for inviting me. It's been a pleasure.
You're welcome. And so the next seminar will be in 2 weeks. The speaker will be Irene Cavallari. So thank you to everyone for attending this seminar, and see you in the next seminar.
See you.